Hey guys! In this video I'm going to give you an overview of using Laplace transforms and partial fraction expansion to solve ordinary differential equations. So let's suppose you have some sort of system, such as an elevator or a motor or a rocket, and you want to find out what the output would be in response to some input for your system. So let's say we have a rocket, and we want to know what that rocket system is going to do if we give it some sort of input. So this is a roadmap that my professor gave me that hopefully will help you better understand the process and the steps that we take to solving these types of problems. So first of all, you start off with a differential equation. And this is an equation that describes the system of the behavior, and it is usually in the time domain. So in order to solve this problem, we want to use Laplace transforms to convert our differential equation from the time domain to the Laplace domain. And that will give us a transfer function. Now, for the sake of my videos, my transfer functions will be some sort of polynomial over another polynomial. And at this point, we can take and multiply some sort of input by the transfer function. And it's important to make sure that the input is also in the Laplace domain before you multiply it. And so then, assuming that our expression is in both normal and proper form, we could perform partial fraction expansion if we didn't want to do integration. So when you do partial fraction expansion, you will usually have a right-hand side that looks something like this. And essentially it will be either one or a couple or like several fractional terms added together. And what's important to note is that the denominators in our fractional terms are related to the characteristic polynomial of our expression. And so when we perform partial fraction expansion, we will be solving for these unknown numerator terms here, which are called the residues. And so once we've solved for the residues, we can take and substitute them back into this partial fraction expansion and take the inverse Laplace transform to return to the time domain and obtain our output in response to our input. Okay, so partial fraction expansion is used to convert the expression for the output to a form which we can use the Laplace tables to do the inverse Laplace transform. And as I mentioned on the previous slide, this is one way to solve for the output when you don't want to do integration. So for the sake of my videos, our transfer functions will be a polynomial over a polynomial. And so n of s represents the polynomial in the numerator, and d of s represents the polynomial in the denominator. And it's also important to note that s is like the Laplace variable, and that denotes that we are in the Laplace domain. Okay, so real quick, if I go back to this slide, for my videos, I am going to start my examples right here with the transfer function. So it's important to note that we start here at step 3 and then move forward to the end. But like in the real world, you could be given, like I said, some differential equation in the time domain, and you would have to start here at step 1 and move forward. Okay. So this is just a expanded version of what our transfer function might look like. And I'm going to use this to help you better understand what I mean by proper and normal form. So for proper form, the maximum power of the numerator must be less than the maximum power of the denominator. So, okay, real quick, B and A are just some arbitrary constants or variables that I picked to represent arbitrary constants in front of each of my S power terms. Additionally, M represents the maximum power term in the numerator. And N represents the maximum power in the denominator. So with that being said, what proper form means is that M has to be less than N. And for normal form, the coefficient of highest power of S in the denominator must be 1. So if N is representing the maximum power in the denominator, then A of N is the coefficient of the highest power in the denominator. And therefore, in order to be in normal form, A of N has to equal 1. And it's important to make sure that your expression is in both proper form and normal form before you proceed with partial fraction expansion and solving your problem. Okay, so next I have a couple examples to hopefully help you better understand proper and normal form. So let's look at example 1. I see that the maximum power in the numerator is 2. And the maximum power in the denominator is 3. So therefore we are in proper form because 2 is less than 3. And then I also see that the coefficient for my s to the third term is 1, and so therefore we are in normal form because the coefficient in front of the highest power of s in the denominator is 1. So at this point, if we wanted to, we could proceed with partial fraction expansion and solving our expression. Okay, example 2. So again, I am in proper form because 2 is less than 3. However, I am not in normal form, because the coefficient in front of my maximum power s term in the denominator is 7 instead of 1. So I can go ahead and do some mathematical manipulation to put this expression in normal form so that I can proceed with solving it. So the first thing I'm going to do is pull the 7 out of the denominator. Okay, and now I'm going to take and pull a 1/7 out of the entire fraction. And last but not least, I am going to distribute this 1/7 into the numerator And this is just to simplify the expression for later on when we perform partial fraction expansion and we're taking the inverse Laplace transform. It's just to make our lives easier so that we don't have to worry about this constant just hanging around on the outside. So I will get something that looks like this. This is now in both proper and normal form. So again, if we wanted to, we could proceed with the rest of partial fraction expansion and solving for the output. Okay, so one more example. Okay, the first thing I notice is that we are already in normal form because the coefficient on our s squared term is 1. However, we are not in proper form because the highest power in our numerator, 4, is larger than the highest power in our denominator. So because 4 is greater than 2, we are not in proper form. And at this point, there isn't anything we can do to convert this expression to proper form, so we could not proceed with partial fraction expansion. So this is just something important to check before you actually go through and try using partial fraction expansion. Okay, so the last thing I want to talk about is the unit step. When I took this class, we always used one-sided Laplace transforms, and that is very important because once you obtain your output expression, you need to multiply by the unit step, and here's why. So let's say we have some function, and let's say the horizontal axis represents time. So therefore, for t is less than 0, we have a parabolic, or not, the whole thing is parabolic. We have some values other than 0 for time is less than 0. And then for time is greater than 0, our function values are, again, something other than 0. So in order to use the one-sided Laplace transform, we need all of our function values for time is less than 0 to be 0. And this is where we introduce the unit step. So this is what a unit step function looks like. And as you can see, for time is less than 0, our function value is 0. And for time is greater than 0, our function value is 1. So if we take this function and multiply it by the unit step, we will get something that looks like this. And as you can see, our function value for t is less than 0. That does not look like a t. T is less than 0. Our function value is 0. And then for t is greater than 0, our function value is not 0. It just is doing whatever the function wants to do. Okay, one more example of this. So I think that this was this is a cosine function. And so as you can see, for t is less than 0, we have a wave. And then for t is greater than 0, we also have a wave-looking function. So in order to use the one-sided Laplace transforms, we need to get rid of this wave, and it needs to be a function value of 0. So we introduce the unit step and we multiply them together. And now we get something that looks like this, where for all time is less than 0, our function value is 0. And for time greater than 0, our function value is doing whatever our happy little function wants to do. So when you're solving these problems, which I have some examples in other videos, and you get your output, you'll usually get something that's like x of t equals some sort of expression. And you're going to want to multiply the entire expression by u of t. U of t is our unit step function. And what you're doing is you're going from this to this by multiplying by this. So that's it. I hope this video helped you guys better understand how we can use one-sided Laplace transforms and partial fraction expansion to solve ordinary differential equations.